Okay, second section here in chapter 8. Yesterday we talked about ionic bonding. Today we're going to start talking about covalent bonding. Hopefully you remember that when we talked about ionic bonding, we talked mainly about ionic bonding being between a metal and a non-metal, and that typically what you find in an ionic compound is that you have these large lattice structures, and we talked a little bit about lattice energy and what it takes to overcome lattice energy, such as the charges on the ions and the distance between the nuclei. So today we're going to talk about covalent bonding, which is most of the things made up in the world are actually with covalent bonding. Ionic compounds, so metals and nonmetals, they're usually very brittle. They have really high melting points. They do break along those flat surfaces because of those lattice structures that they form. But most substances that exist do not fit into that category, such as water, gases, plastics, etc. And so there's a different type of bonding that we use to describe these types of bonds, and that is called a covalent bond. A covalent bond is a chemical bond formed by sharing, the big difference there is sharing electrons. And one thing I didn't include here, which probably I should have, is that in covalent bonding, it's typically between two or more non-metals. And if you look at the periodic table, there's not a lot of non-metals that it could be because we're talking about bonding. So typically, you've got your periodic table here, and you've got the stair step here that separates the metals from the non-metals. So none of these are in because they're all metals. The ones along here don't count either because they're metalloids. The ones at the bottom, the F orbital, don't count because they're metals. The noble gases don't count because they typically don't form bonds. Xenon can form a few bonds, but not many. So really, we're only talking about carbon, nitrogen, oxygen, fluorine, and then going down, phosphorus, sulfur, and chlorine, and then selenium and bromine, and iodine, and then obviously hydrogen over here. So we're not talking about a ton of elements that can form covalent bonds. It's really these ones here and hydrogen. So we're talking maybe 10, 11 elements that do form covalent bonding. Okay, but there's many trillions upon trillions of ways that these, 11 or 12 elements can combine with each other to produce different chemical properties and all of that. So even though there's very few elements that do form covalent bonds, they combine in such a variety of ways that there's a ton of different ways they can form molecules. So hydrogen is a very simple example of covalent bonding. Here we've got a hydrogen proton and another hydrogen proton. Here's the electron density of the electrons. And we can see that these electrons are shared evenly between the two nuclei. We don't see one electron, the two electrons farther over here or farther over here. We see that they're shared equally between both atoms. Now, with covalent bonding, you can actually have individual molecules. Remember with NaCl that we say NaCl, but when you have NaCl, what you've really got is you've got a whole bunch of sodium and chlorine ions surrounded by other sodium and chlorine ions. Whereas with covalent molecules, you can have just a single H2O molecule floating around, and you can have a single carbon dioxide molecule floating around. Okay, and so what we can do is we can actually, just like how I just did, you can actually draw these structures. When you draw what that molecule looks like, you're drawing a Lewis structure for that molecule. Okay, and notice here that when I did that, these lines here, that dash, those represent a bond. And a bond is simply an electron from one atom and an electron from another atom being shared between the two. And the one way that we determine, first of all, how many bonds it's going to make, it does depend on the number of valence electrons. And just like how we saw before, the number of valence electrons depends on where it is on the periodic table. Group 1, so the alkali metals have 1 valence electron, 2, and then 3, 4, 5, 6, 7, and 8. So that the one thing you have to be able to do is you have to be able to look at carbon and go, carbon has 4 valence electrons, or look at selenium and go, selenium has 6 valence electrons. Depending on where it is on the periodic table, the valence electrons play a big role. And if we look at like fluorine or chlorine or something like that, they only tend to form one bond because they only need one more electron to become like a noble gas. Remember when we talked about why atoms react, and it's because they want to become more stable. And the noble gases are the most stable elements on the periodic table. So fluorine just tends to form one bond because with one bond it gets one electron, becomes like a noble gas. The oxygen group tends to form two bonds, nitrogen 3 and carbon 4. But again, these are not hard and fast rules. These are, oxygen will many times only form one. Carbon does tend to form typically 4 every time, and fluorine does tend to form 1. Okay, if you are just sharing 2 electrons, so you've got a 1 hydrogen and 1 hydrogen, and you've got 1 electron here and 1 electron here, and you form that bond, that is a single bond. And it's when you have 2 electrons sharing those two atoms, sharing those 2 electrons. Okay, if you have 2 electrons from each one being shared, for example, in CO2, you have what are called double bonds. Now, you don't necessarily have to have 2 of them, but like an O2 molecule is another example of this, where you have this is a double bond here, where 4 electrons are being shared between the 2 atoms. And we'll talk about why those form here in a little bit. And then a triple bond occurs. A nitrogen molecule, it consists of a nitrogen-nitrogen triple bond. Okay, then more bonds, so the triple bond, the shorter their distance and greater their strength. So a triple bond is shorter and stronger, whereas a single bond is weaker and also longer. There's more distance between the nuclei. So how do we draw a Lewis structure? There's 5 steps. They're not too difficult. But to draw one, there's 5 things we have to do. The first thing we have to do is we have to count all the valence electrons for the entire molecule. Okay, so if you have CO2, you look at the periodic table and go, carbon has 4, oxygen has 6, but there's 2 of them, so that's 12, and 4 plus 12 is 16. If you have a negative charge, you add 2 more electrons. So like on SO4 2-, you'd go sulfur has 6, oxygen also has 6, but there's 4 of them, that makes 24. 6 plus 24 equals 30, plus those 2 makes 32. So you don't add it to the oxygen, you just add it to your overall total. If you have a positive charge, like NH4 plus, then you take 1 away. So 5 plus 4 equals 9, and then subtract that 1, makes it 8. Okay, so you've got the number of valence electrons, and then step number 2 is you have to put 1 atom or multiple atoms in the middle, and then put the other atoms around that atom or those atoms. Typically, if you have carbon, carbon will always go in the middle. Okay, usually this is not very difficult. Okay, on the AP exam, usually the one that comes first in the molecule will be the one that goes in the middle. Okay, but if there's, like in this case, like PF3, you can't put 3 fluorines in the middle, so obviously the 1 phosphorus has to go in the middle. So it's really just using common sense. What you might find is something like this. You might find like C2H6. In that case, you would have 2 atoms in the middle. You would have 2 carbons acting as the central atoms, and then all of the hydrogens would just go around the carbons like that. So if you had like C3H8, all 3 carbons would go in the middle, and then again the hydrogens would just circle around that. So like that. Okay, but typically there's just 1 atom that goes in the middle, and then everything else goes around it. Okay, and then once you have your 1 in the middle, you've got the other ones around it, you place a single bond between the central atom and each surrounding atom. So you've got your, let's say CH4, you've got your carbon, and then you place a single bond between them. And then if you need to, let's look at like SF4. So we put 1 in the middle. We've got the 4 fluorines, not hydrogen. You've got the 4 fluorines around it. And then it says complete the octet for each surrounding atom. So I'm not worried about sulfur, but I have 34 electrons all total on SF4. So I'm going to complete the octet for the outer atoms. And I've done that. Okay. Okay, a couple of important things there. Make sure you keep track of the number of electrons you've used. So for example, here I've used 8 on each one. So 8 times 4 is 32. So I've got 2 left. You definitely want to make sure that you keep track of your electrons. And don't forget that if you have hydrogen, such as right here, the hydrogens don't get dots on them. Hydrogen makes a bond and that's it. And then if you do have electrons left over, you have to place them around the central atom. So like on SF4, we completed the octet for the fluorines, but then we had 2 left over. So when you do that, you have to put the extra ones on the central atom. Okay, water is an excellent example of that. Water, H2O, 8 valence electrons. The oxygen goes in the middle. You can't have 2 hydrogens in the middle. With the oxygen in the middle, I've used 4 electrons, but I've completed the octet out here. So I have 8 minus 4 equals 4. I have 4 electrons left over. So 1, 2, 3, 4. Anytime you have electrons left over, you must place them around the central atom. And then the last step is, and this is where double bonds come into place, that if the central atom, once you're done and you've run out of electrons, if the central atom doesn't have 8, then you must. So if the central atom does not have 8 electrons, you have to make double bonds or triple bonds with the outer electrons to make the central atom have 8. Okay, so let's take a look at here. Here's a couple of examples here. I'm going to throw a couple more in here. Let's do CO2 so you can understand that as well. And that's a pretty good summary there. So CF4. So let's take a look at CF4. CF4. Carbon has 4 valence electrons, fluorine has 7, and there's 4 of them, so that makes 28. So we've got 32 electrons all total. So we put 1 atom in the middle, put the fluorines around it, place a single bond between the central atom and the outer atoms, and then I complete the octet for the outer atoms. And I've got 32 electrons here. What the heck that's an F, right? I don't know what that is there. And I've only got 32 electrons, so I'm out. I have no electrons left over, so I don't put anything on the carbon in the middle. The carbon already has 8, so we're done. So a CF4 molecule looks just like that. Now, does it have to be the F's in that direction? No, you can have them. You can have carbon and then the fluorines, left, down, and then up, left and right, and up and down. PF5 actually is very similar to CF4, but you'll notice that with PF5, you put those 4 fluorines on and you go, oh no, how can I do this? Because phosphorus is going to have more than 8 electrons. It's okay. You don't have a choice. You certainly are not going to have something like this because fluorine's not going to make 2 bonds. Okay. In general, it's going to be one atom is going to be in the middle, and the other atoms are going to circle that central atom. And then we've got 40 electrons all total. So again, 8 around each one. So we've got a total of 40. The phosphorus does have more than 8, but we don't have a choice. So we just continue with that. SF4 is a good example in that sulfur has 6. Fluorine has 7. There's 4 of them. That's 28. So we've got 34 electrons. So 34. So we're going to have 32 electrons. And so we've used 32, and we've got 2 left over. So those last 2 is where step number 4 comes in, where you have to take electrons that are left over and place them on the central atom, even if it means making more than an octet, which it does in this case. Okay, so we're done. Now the last one, CO2. So CO2, carbon has 4, oxygen has 6. There's 2 of them, that's 12. That makes 16. So we've got carbon, oxygen, oxygen, a single bond, And you'll see here that we've used all 16 of our electrons. We have none left over. So the central carbon does not have 8 though. So that's where we have to come in, take our 2 that were out here and put them into here. Because by doing so, it still leaves oxygen with 2, 4, 6, 8 electrons. But now carbon has, again, 2, 4, and now it has 6 electrons instead of 4. So now what we need to do is we take another 2 and move those 2 into here. Because when you make a double bond, not a triple bond, sorry. When you make a double bond, that bond still counts for the outer atom. So oxygen here has 2, 4, 6, 8 electrons. But now the carbon has 2 on this side, 2 on this side to make a total of 8 electrons. So we can see that by making the only time, and this is important, the only time you're ever going to make double or triple bonds is when the central atom does not have 8 electrons. Do not make double or triple bonds unless the central atom is missing its 8. If it is and you've run out of electrons, then you pull electrons from the outer atoms and you move them in. Okay, so there's your review packet. Notice there's no book questions because there are a lot of Lewis structures to draw from old exams. So just do these, please, and we'll talk about them tomorrow.